Now I want to talk you through interpreting some plots, some visual representations of constant acceleration situations. Now one thing to note is that we can apply this to situations where you have regions, so a piecewise function, where each piece has a constant acceleration. So note that this plot is of acceleration. And so initially, for the first 6 seconds, we have a positive 1 meter per second squared acceleration. Now, our object after that point suddenly has an acceleration of negative 2 meters per second squared. So again, keep track of your signs, as that's going to represent, in this case, since this is x, acceleration to the left versus acceleration to the right. Note that I am not saying speeding up or slowing down, as we actually need information on which direction our velocity is to know that. So initially, if I just want to say that we have our x coordinate system, this is going to be my positive x direction. So a positive acceleration is going to be an acceleration vector that points to the right. This is going to be an acceleration vector that points to the left. Again, not saying that my motion is that way, or even that my velocity or my position are that way, just that that's what the acceleration is. So now we can say, okay, if I want to get what my velocity is, one, I have to know what my initial velocity is. Second, all I need to do then is integrate this. Another way to think about it is for constant acceleration, uniform acceleration, I expect to have a straight line where the slope of the velocity line is given by this acceleration. So if I pull up that plot, now again in the problem you would probably have this object as being described as starting from rest. Otherwise you would perhaps be told what the initial velocity is. So please make sure that you look for that. So note that initially we have a straight line and our slope is 1. After 3 seconds it's going 3 meters per second. Now at 6 seconds, the slope changes suddenly. Now one thing to be a little bit careful is that this is our model. Our model is uniform acceleration, that really the only way we can do this easily is if acceleration are these nice horizontal line segments. Now in math, obviously you can do functions like this, and students have asked me before, how do you draw, those open or closed dots? We don't ever worry about that. And one of the reasons we don't worry about that is that in the real world, things cannot actually change this suddenly. So for instance, one reason that this might happen is because the forces that you've applied to it have changed. Someone has stopped pushing on it or is now pushing on it in a different way. And that just doesn't instantaneously happen. However, it's really hard to model those small changes that would make this a curved line. So this is where we're making a reasonable simplification to model it as constant acceleration, even though in the real world it would be a little rounded on the edges. So be careful and make your velocity plot directly from what your acceleration plot looks like, and don't artificially round this because you think that it shouldn't be sharp. Again, in the real world it wouldn't be, but we want to make simplification so that we can do the physics better. So at 6 seconds and later, we have a negative value for acceleration, which means that our slope is negative. Now this is one of the things that's really important to notice, is that here we have a positive slope, here we have a negative slope, but the value of the slope is steeper here. So it took 6 seconds to go from 0 to 6 meters per second, then it only takes 3 to get back to 0. So I want to label a few points. So here, it's actually stopped. Now, one thing to note is that this doesn't mean that it's returned back to its original position. We would need to do an integral for this. And in fact, remember that position is coming from doing the integral. This entire time, it's moving away from wherever it started. So not only is this stopped, this is also the maximum displacement. But now, at this point, its velocity is it's moving to the left. So it's gone out and turned back around. So that's the situation. It's important to note from the acceleration curve alone, you know how the acceleration changes, but you wouldn't have known the point at which it has stopped moving. That isn't denoted here at all. The acceleration is constant in this region, but our object stops moving the moment that this line crosses 0. So that's one reason why you would want to actually draw this velocity plot. Now we would have to then actually figure out where the area under the curve is 0 to know when it comes back and reaches its initial. So briefly, this is the motion diagram that corresponds to what we have up here, that our object started from rest and had a constant acceleration to the right. So it's speeding up and it's moving to the right. Now at 6 seconds, it has its maximum speed, and at this point, the acceleration is now pointing to the left. So our object doesn't immediately start moving to the left. It still has a velocity that is to the right. It still has a positive velocity, but now it's slowing down. This right-pointing velocity has a left-pointing acceleration. That means it's slowing down until it stops. Now what we typically do is break this motion diagram into 2 pieces so that we don't draw it over top of itself. But now after this point of 9 seconds, it's now moving to the left, and it has an acceleration vector that also points to the left. So here, it has a velocity to the left, acceleration to the left, so it's speeding up. So at 12 seconds, it's actually back to the position it was at 6 seconds, and the reason for that is that if you note, we have this positive area under the curve here, this negative area under the curve there, and they obviously cancel. And so the position here and the position there is the same. The displacement from 6 to 12 seconds is 0. Now after 12 seconds, it isn't shown, but as long as this acceleration is uniform, what's going to happen is our line, and I'm not very good at drawing straight lines, is going to just continue downward. So it's going to keep speeding up faster and faster, but continue moving to the left. So we've already talked a little bit about how to relate calculus to the plots that we're looking at. And again, remember that when we have our acceleration, we would integrate this to get our velocity. So the integral of a horizontal line, or a constant, is a straight line, where the slope of this was our acceleration. Now again, remember that we can't get our initial value from this. So the initial time, the initial velocity, may or may not be equal to 0, but really it's that straight line that we learned something about from this. So potentially this point is over here, but you would have to be given more information in the problem to actually know about this. So what if we wanted to move on and actually go now all the way to position? So this is where you think back to plots that you've been shown, I think, a few times at this point before, and we've seen this straight line velocity plot before. And that corresponds to a parabolic position plot. So to just talk you through this, if we have a constant acceleration that looks like a horizontal line in acceleration plot, that's a straight line, but not horizontal, where the slope is given by the acceleration in velocity versus time, but that corresponds to a parabolic plot in position. So if you see a parabolic curve in position versus time, that is likely corresponding to a constant acceleration. And I say likely because it's sometimes hard to gauge if this is perfectly a parabolic motion or not by eye, but I'm not going to try to trick you by giving you something that's just slightly shifted from a perfect parabola and asking you whether it's constant acceleration or not. So if it looks like a parabola, you probably can assume that it is, and parabola in position means uniform or constant acceleration.